So now today we are going to look at the bin problem, which can be solved in, using the approximation algorithm. So let me state the problem, then we will look into the solution. The solution is not very difficult. Actually, you know that already. So the problem is like this. You have n items of sizes A1, A2, A3, etc. An, where the A1, A2, A3 is less than or equal to 1. So the size of all the item are less than 1. That means it may be 0.1, 0.5, 0.7, like that. So you have to pack it in a unit size bin. So it can contain only 1 unit, where the items are of 0.1, 0.5, below 1. So you have to pack it of size 1 unit bin. And you have to use here the optimization objective is you need to use less number of bins. Okay, so is the problem clear?
Yes.
ma'am.
Okay.
Yes, ma'am.
Okay, then solution also not very difficult. So what do you think? What can be done? How we can proceed? Suppose you are having 5 items: 0.5, 0.8, 0.3, 0.1, 0.7. So how you think you can pack it? We are having 0.8, 0.3, 0.7, 0.2, 0.5. How do you pack it? Hello? Hello?
Yes.
How
Yes,
do you
ma'am.
pack it? How do you pack it?
Starting with biggest number, ma'am.
Okay, so I'll take 0.8. Then what do we do? Shall I put 0.3? I cannot put. So this bin cannot contain that. So what do I do?
We'll move on to the next.
Okay, so let me put in the second bin 0.3. Okay, now what do I do? So shall I put the next one 0.7?
Yes, ma'am.
And then third bin will contain 0.5. Is it the solution that you can think, or there can be some other way by which can be done? So now here I need 3 bins. Yes, no? The numbers that I have taken happens to be 3, having only 3 bins. Okay. So suppose I say I have one more 0.1 to be added with this. What do I do? Where do I put? Let me put in A or B or C. That the last one, which is of the weight 0.1 or the dimension 0.1. Where do I put? First A or B or C?
C, ma'am.
C. Why can't it be in A?
Because C value is larger than C.
A value is larger than C. But it can contain 0.1 also over there, no? Okay, somehow we have to form some uniformity. So what you said, you go with the biggest number, okay, and then put that. Then the next biggest, if I look at it, then 0.7, that will go into the next bin. Then the next bin will contain 0.5. Then I will be having problem of where to put this 0.3 and 0.2. Do I need to reuse this AB and or I can use the C? So that is left to you. You can follow in any order. So there are 3 ways by which they have solved it. So the first idea is see here he has given a different example 0.3, 0.2, 0.2, 0.2, 0.4, 0.5. So here's put the 0.3 plus all the 2's together, then 0.2, 0.4 in another bin. 0.5 cannot get into this, so he has to go for a new bin. So this is one solution that they have provided. How when he looks at it. So now another way to look at the same problem, see 0.5 and all the smaller things have gone to the second bin and 0.2 and 0.3 have gone here. So with the two bins, they were able to achieve. So this is a better solution or this is an optimum solution, but this is a solution that we have given or the earlier we have thought of. So the algorithm is the first fit algorithm. So what we do in this is place the item in the order in which they arrive. No change in the order. Place the item into the next lowest number bin in which it fits. And if does not fit, open a new bin. Okay. So now when you look at it, 0.4, it will go into this. 0.8 cannot get into this. So you have to open a new bin. So put it in 0.8. In the second bin. Then you have a 0.5. It can fit in the first bin itself. Put it. Next one, 0.1. That can be accommodated in the first bin. So put it. The next one is 0.7. 0.7 cannot be accommodated in the second bin because it can contain maximum 1. So that means you are left with only 0.2. So you go here. So we put it in the third bin. So now the next item is 0.6. So it cannot fit in here. This is over. It cannot fit here. It cannot be fit in here. And this cannot contain that also. So I have to go in for, I have to come here and put in this. Then the next item is going to be 0.1. So this is over, so I cannot put it. So this is not over. Still, I am left with 0.2. So I can put it here. So then the next 0.1 comes here. The next item is 0.4, which cannot go into the second bin, third bin. So it has to go into the fourth bin because you have only 0.6 already. So it can become full. Then the next one is 0.2 comes, we cannot accommodate in the second bin. So I have to put it in the third bin. And the next one is going to be 0.2. So it cannot be accommodated here, not here because it's 0.9. This is over. So I have to create one more. So this is what first fit is. As it comes, you put it in that order. If it is possible for you in the, accommodate in the lowest, you accommodate. Otherwise, go to the next. If it's not possible, go to the next. So if all are exhausted, open a new bin. So this is what we call it as first fit. Have you studied this algorithm somewhere?
Operating system.
Yes, very good. So the same idea only. So from here they have taken over to over there. So but so the first fit is a page demand paging or in your page algorithm. That's the first fit, and of course the amount of time that it is going to take. Actually, actually I call it as a two-factor algorithm because the if the C star is going to be the optimum solution and our algorithm uses C bins, then at least C minus 1 bins are more than half full. So that means my C star is the optimum solution is greater than or equal to sigma AI. AI is nothing but the weight, the total weight. It is greater than or equal to C minus 1 by 2 because it is half full only. So total weight will be less than that. So which implies it's just a numerical. So this you take it over there. So and then that means 2 C star is greater than C minus 1. So that means actually the difference between actually the ratio if you find C star by C will be equal to 2. So hence that's why we call it as that epsilon I have defined now. Here it happens to be or the K that we have defined in the initial thing. So it happens to be 2 less than or equal to 2. So the next algorithm we can use is going to be the next fit algorithm. So place the items in the order in which they arrive. Place the next item into the current bin if it fits. If it does not, close the bin and start a new bin. So now how it varies. 0.4 will go into the first bin. Then actually 0.8 it cannot fit in, so open a new one, so it will come here. 0.5 cannot fit in this, so it will go for the next one. 0.1, the same bin, it can fit it. But 0.7, here it is 0.6, so you can put only 0.4 over here, so it has to open a new bin. So like this it goes. So if you look at it, what happens, you are using more number of bins compared to whatever we had earlier. So the next bit algorithm will not really perform well compared to first bit algorithm. Is it okay? Yes? Okay.
Yes, ma'am.
Yes.
Okay. Then the best fit algorithm. So what we do in this is place the item in order in which they are, right? Place the next item into the bin which will have least room left over after the item is placed in the bin. That means the remaining should be less than, actually as such it should be as minimal as possible. If it does not fit in any bin, then start a new bin. Okay. So now 0.4, no change. So you put it here. And then 0.8 cannot hold here. So you open a new bin. So you open the second. Then you have got the third one that is going to come in. So the third one is going to be the 0.5. So the 0.5 when you are going to take it, so the 0.5 will be able to fit in here, and actually the wherever you are going, you are having two bins or you open at a time. So here it is 0.8, here it is actually 0.4 only you are having, you can fit it here, so you can have here. The next one happens to be 0.1. 0.1 can be put here as well as here. But the thing is, how much is remaining? Here you will have one remaining, whereas here you will not have anything remaining. So I prefer to put it here rather than in the second bin. Is it okay? Then 0.7, obviously it cannot fit here, so open a new bin. 0.6, I cannot fit in here, so you open a new bin. Then 0.1, where should I put? It cannot be put here. So it can be put here or here or here. The thing is, I prefer this over the others because it will leave very minimal over. So I prefer this. So then the next one is 0.4, cannot fit here, cannot fit here. So I have to put obviously over on this. Then 0.2, I cannot put it here. I can put it here, so that comes here. Then the last one, 0.2, it cannot fit here, it cannot fit here, so I have to, this is over, so I have to go for that, go and open that next. So this is what we call it as the best fit algorithm. Okay, so all these, the best fit, next fit, and first fit, all almost two approximation algorithm only. It cannot be giving less than that. So that's why actually both all are almost doing, in terms of analysis, when you look at it, they behave only in the similar way. So there is no change in that. So we have seen 3 examples can be solved using an, we have solved as an approximation algorithm. The first one we have seen is, what's the first one we have seen? What's the first one we have seen, ma'am?
Vertex cover algorithm.
Yes?
Vertex cover algorithm.
Vertex cover.
Vertex cover. And your before that?
Approximation algorithm.
So in that first problem,
Adi, we have to try.
coloring problem. Yes? Coloring problem was very, very simple. No, I said if there is going to be a graph which does not contain any edge, return 1. If it is going to be a bipartite graph, return 2. If otherwise, return 4. That's it. So simple that was. So that is also an approximation algorithm. We have seen the vertex cover problem. We have seen the traveling salesman problem, and the Last one we have seen is the bin problem. So almost all the algorithm which has the time upper bound to be the exponential time algorithm can be thought of solving using this approximation idea, because we cannot find the optimum solution at any point of time because it will be running indefinitely. So it will take such a long time. So better we go in for these kind of approximation algorithm till we find a technique by which we can examine all possible cases in just a fraction of a second. So till then, we have to wait for the technology. So it may be a quantum computing which can give an answer for that when we want to compare things. So that may be a better option. We don't know. So still some other technology arrives. So we have to be happy about these kind of algorithms which gives at least some solution rather than